We have our winner, logistic regression. But a model straight out of the box is rarely at its best. So now we tune it. Tuning means adjusting the model's settings to get the most out of it. And there's one rule we never break while we do it: we do not touch the test set. First, an important distinction. There are two kinds of numbers inside a model. Parameters are the coefficients the model learns from the data on its own. We don't set those by hand. Hyperparameters are the dials we choose before training even starts. Tuning is the search for the hyperparameter settings that score best. And crucially, we judge those settings on validation data, held out folds, never on the test set. Here's the golden rule, and it's worth saying slowly. The test set stays sealed the entire time we tune. We can slice the training data into train and validation folds and experiment there as much as we like. But the moment we start picking settings by peeking at the test set, that test set stops being an honest estimate of the future. So we tune on validation folds only, and we open the test set exactly once, later, at the very end. The first dial is the regularization strength, which we'll call lambda. Regularization adds a penalty for large coefficients to the loss. Turn lambda up, and the model is pushed to keep its weights small and simple. Turn it down, and the model is free to chase every little wiggle in the training data, which risks overfitting. Too little, and we overfit. Too much, and we underfit. So we search for the lambda that scores best on the validation folds. Let's actually run that search. Each point is the real validation AUC at one value of lambda, computed with cross-validation. And here is the honest result. It barely moves. We start at about 0.768 with no penalty, nudge up to roughly 0.770 with a small penalty, and then it slips as we penalize too hard. That's a genuine lesson, not a disappointment. The pattern in this data is already close to a straight line, so regularization is a safety net that guards against overfitting, not a magic switch that boosts the score. We'll keep a small, sensible value and move on. The second dial matters far more here: the decision threshold. The model doesn't output approve or decline. It outputs a probability of default, somewhere between 0 and 1. To make an actual decision, we pick a cutoff. Above it we decline, below it we approve. By default that cutoff sits at 0.5. But stop and ask, why 0.5? Nobody chose it for our problem. It's just the number that comes out of the box. And our problem has a very lopsided cost. Remember the two mistakes. If we approve someone who then defaults, we lose the whole loan, $5,000. If we decline someone who would have repaid, we only lose the interest we'd have earned, about $1,000. A missed defaulter hurts 5 times as much as a false decline. That imbalance tells us something. We should be quicker to decline than a neutral 0.5 cutoff would ever be. So let's put a price tag on every possible threshold. For each cutoff, we count the false approvals and false declines on our validation predictions, multiply by their real dollar costs, and plot the total. Watch the curve draw itself. It's a U-shape. On the far right, the threshold is so high we approve almost everyone, and defaulters slip through. On the far left, it's so low we decline almost everyone. Somewhere in between is the sweet spot. Now let's read the curve. At the default 0.5 cutoff, our expected loss is about $413,000. But the curve bottoms out much further left, at a threshold of about 0.20, where the expected loss drops to roughly $275,000. That single change, sliding the cutoff from 0.5 to 0.2, saves around $138,000 by catching more of the expensive defaulters. Same model, same data. We just stopped using the wrong cutoff. You might think, if lower is better, why not push the threshold all the way down? Because the curve turns back up. Go too low and we start declining almost every applicant, and those $1,000 false decline costs pile up faster than the defaults we prevent. The minimum is a real trade-off point, not a case of lower always winning. That balance is exactly what the curve found for us. Let's lock it in. Hyperparameters are dials we set, and we tune them on validation folds, with the test set sealed the entire time. Regularization here gave only a tiny bump, because the signal is near linear. The real win was the decision threshold. Moving it to match our lopsided costs saved well over $100,000. We've made every choice we can without ever looking at the test set. Next, we finally open it, for the one honest number that tells us how the model will really do.